On October 10, 2024, a coronal mass ejection slammed into Earth's magnetosphere at over 1.5 million miles per hour. And for 6 hours, grid operators across North America watched their transformers heat up in real time. Nobody died. No city went dark for long. But the margin between a quiet news day and a continental blackout was measured in single-digit gigawatts of unused capacity. This video is about the people whose entire job is watching a star 93 million miles away so that your lights stay on. How they do it, what happens when they get it wrong, and the one number you should be watching from now on. That's the whole story, in about 18 minutes. Here's the question nobody asks until it's too late. Who is actually responsible for the electrical grid when the sun misbehaves? Not the utility company down the street. Not your local power authority. A small, specialized group of forecasters, split between government agencies and private contractors, staring at solar imagery the way a hurricane center stares at a spinning mass over the Atlantic. That is the space weather forecasting community, and most people have never heard of it. Consider what the sun actually does. It's not a stable, quiet ball of light. It's a churning, magnetically tangled reactor that occasionally throws billion-ton clouds of plasma directly at us. That's a coronal mass ejection. When it's aimed at Earth, it takes anywhere from 15 hours to 3 days to arrive. And when it does, it doesn't just light up the sky. It compresses and distorts our planet's magnetic field. That distortion induces electrical currents in anything long and conductive on the ground. Power lines, pipelines, railway signals. That is the entire mechanism, and it is almost embarrassingly simple physics once you see it laid out. A moving magnetic field induces current in a conductor. Your grid is one of the largest conductors humans have ever built. Here is the single most important thing to understand about this threat. It's not really about the storm in space. It's about what that storm does once it reaches a transformer built for regular alternating current, and instead gets hit with something closer to direct current. Geomagnetically induced current pushes transformers into a state called half-cycle saturation. In plain terms, the transformer starts trying to do a job it wasn't built for, and it gets hot. Not warm. Hot enough to damage internal windings. Hot enough to release gas. Hot enough, in extreme cases, to fail permanently within hours. And large power transformers are not something you order off a shelf. Custom units can take 12 to 24 months to manufacture and ship. That is why a solar storm isn't just a weather event. It's a supply chain event, wearing a weather costume. Now, bring that back to the forecasters. Their job isn't to predict sunspots for fun. It's to give grid operators a lead time window, usually somewhere between 15 and 90 minutes. Once a storm is confirmed inbound by satellites parked a million miles from Earth, to make operational decisions, reduce load, reconfigure transmission paths, take vulnerable transformers offline before the current spikes, not after. That's the entire value of the warning. Not stopping the sun, buying human decision makers a small, precious window to act. And that brings us to the case study that the entire modern industry is built around. March 1989. Quebec. A coronal mass ejection reached Earth and triggered a geomagnetic storm that induced currents strong enough to trip protective relays on Hydro-Quebec's grid. The province's entire power system collapsed in about 90 seconds. 90 seconds. 6 million people lost power, some for over 9 hours. In the middle of a Canadian winter. Transformers as far away as New Jersey were damaged. That event became the reference point, the benchmark, for every space weather protocol written since. But here's the self-correction, because it's important. Quebec, 1989, is often treated as the worst-case scenario in popular explainers. It isn't. It's the worst confirmed modern case with detailed engineering data. The actual worst-case reference sits nearly a century and a half earlier, September 1859. The Carrington event. A solar storm so intense that telegraph operators across North America and Europe reported sparks jumping from their equipment, some systems continuing to send messages with their power supplies disconnected entirely, running purely on induced current from the storm itself. Auroras were visible as far south as the Caribbean. If a Carrington-scale event hit today's grid, a grid infinitely more interconnected, more digitized, and more transformer-dependent than anything that existed in 1989, the damage estimates from groups like Lloyd's of London and various government risk assessments range into the hundreds of billions of dollars, with recovery timelines measured in months, not days, for the hardest-hit regions. That number deserves a pause. Months. Not a blackout you wait out with a flashlight and a generator. A blackout where the replacement parts for your regional grid are backordered behind every other region asking for the same parts at the same time. Let's talk about the conspiracy angle, because it exists, and it's worth debunking directly instead of ignoring it. There's a persistent claim online that utility companies and governments already know a Carrington-level event is coming on a fixed, predictable cycle, and are deliberately withholding that information to avoid panic or liability. That's not how solar activity works. The sun does follow an approximately 11-year activity cycle, and we are currently past the peak of solar cycle 25, which crested in 2024. But cycle strength predicts general storm frequency, not the timing or intensity of any individual eruption. Nobody, not the National Oceanic and Atmospheric Administration's Space Weather Prediction Center, not any private forecasting firm, can tell you 6 months in advance that a Carrington-scale event is coming on a specific date. What they can tell you is elevated probability during active phases of the cycle. And that's a very different, much less cinematic kind of warning. The real story isn't a hidden countdown. It's a genuine forecasting limitation that agencies are open about, which is arguably more concerning than a cover-up because it means the uncertainty is real. That is why the industry has spent the last 3 decades building physical resilience instead of just relying on warnings. After 1989, and after another significant storm sequence in October and November of 2003, known as the Halloween storms, which knocked out a transformer in South Africa and disrupted satellite operations, regulators started mandating things like geomagnetically induced current monitoring at substations, blocking devices on transformer neutrals, and coordinated storm response plans between grid operators across state and national lines. The Halloween storms are a useful bridge case here because, unlike Quebec, they showed the threat wasn't confined to high-latitude regions near the poles. South Africa is nowhere near the Arctic. That storm proved geomagnetic risk is a mid-latitude problem too, which meant grid planning had to expand far beyond Canada and Scandinavia. So here's where the forecaster actually sits inside all of this. Picture a room, usually windowless, banked with monitors showing solar imagery from spacecraft, like the National Oceanic and Atmospheric Administration's GOES satellites, short for Geostationary Operational Environmental Satellites, and the DSCOVR probe, short for Deep Space Climate Observatory, parked at the Lone Lagrange point, a gravitationally stable spot roughly 1 million miles from Earth, directly in the Sun's direction. That probe is the tripwire. It sees the solar wind and any incoming plasma cloud about 15 to 60 minutes before it reaches Earth, and that window is the entire warning system for the induced current threat. 15 to 60 minutes. That's not a lot of time to reroute a regional grid, and it's the reason so much of the actual protective work happens in advance, not in reaction. The forecaster's daily job is issuing graduated alerts, watches, warnings, and storm-in-progress notices. On a scale from G1 to G5, minor to extreme, that grid operators, airlines, and satellite companies all monitor continuously. Connect that back to your own home for a second, because this isn't an abstract, industrial-only concern. Even a moderate G3 storm can degrade GPS accuracy, disrupt high-frequency radio used by aviation and emergency services, and, in some documented cases, cause voltage irregularities that trip local protective equipment, leading to brief regional outages. A severe G4 or extreme G5 event is where the transformer damage risk becomes serious. And remember, we're currently in the declining phase of a solar cycle that already produced multiple G4 and G5 rated storms, including that October 2024 event we opened with, and a similarly intense storm in May 2024 that produced auroras visible across the continental United States, as far south as Florida and northern Mexico. Beautiful to look at. A visible signature of an invisible current running through the ground beneath your house. Now, here is the checklist. If you want to actually track this risk, instead of just reading about it after the fact, here are the things worth watching. Number 1. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center scale. This is the public G1 through G5 geomagnetic storm index, updated continuously, and it's the single clearest signal of active or incoming risk. Bookmark it. It's free, public, and updated far more frequently than most people realize. Number 2. Solar cycle phase. We're past the peak of cycle 25. But declining phases have historically still produced significant, sometimes surprising, storm activity. Don't assume the risk drops to zero just because the peak has passed. Number 3. Coronal mass ejection alerts, specifically, as distinct from routine solar flares. Flares reach Earth in about 8 minutes, as light and radiation, and mostly affect radio communication briefly. Coronal mass ejections are the slower-moving, much more dangerous mass ejections that carry the magnetic disturbance capable of inducing ground current. Learn to tell the two apart in reporting, because headlines often blur them together. Number 4. Your own regional grid operator's storm preparedness disclosures. Many now publish, at least in general terms, whether they have geomagnetically induced current monitoring and blocking devices installed at key substations. That's a real, checkable resilience indicator, not marketing language. Number 5. Auroral visibility reports at unusually low latitudes. If you're seeing credible reports of aurora at latitudes where it almost never appears, that is a visible signature of a genuinely strong geomagnetic event happening in real time, and it's worth checking the official storm scale immediately rather than just admiring the photos. Here is the honest, forward-looking read on all of this. The grid is more resilient today than it was in 1989. Monitoring is better. Warning windows exist where none did before. And hardening efforts have genuinely reduced risk at major substations across North America and Europe. That's the real, non-hyped version of this story. And it matters. Because the exaggerated version, the one where a solar storm plunges the whole continent into permanent darkness overnight, simply isn't supported by the engineering. But the honest, concerning version is still serious. A Carrington-scale event remains possible at any point, remains difficult to forecast with precise timing, and would still, even with today's improved defenses, likely cause months, not days, of disruption in the hardest-hit regions, with cascading effects on everything from banking systems to water treatment, to hospital backup infrastructure that depends on a functioning grid to even switch over properly. That is the real stakes, stated plainly. Not extinction level, not overnight collapse. A slow-moving, geographically uneven, potentially months-long strain on modern infrastructure, triggered by a storm event we can only partially predict, arriving from a star we cannot control, watched over by a small number of forecasters, whose entire job is buying the rest of us a little more warning time than we would otherwise have. Watch the storm scale, watch the cycle. Those two things, tracked together, tell you almost everything you need to know about where this risk actually stands right now. If this kind of planetary scale hazard is the sort of thing you want explained clearly, without the hype and without the alarmism, subscribe, because we break down exactly this kind of invisible, slow-building risk on this channel regularly. Like this video if you made it this far. It genuinely helps this kind of long-form breakdown reach more people. and share it with anyone who's never once thought about where their electricity actually comes from, or what's standing between that source and their own front door.